The other thing that's very distinct about the tropics are the waves. These are basically like the convective heating can act as somebody pulling a rope that is tied at one end and send off these waves. We will learn more about these as we go forward. There are specific dynamics which create waves that propagate east and that propagate west, and then they are Doppler shifted because of the background flows, and the ocean is much more restricted in terms of how the waves can travel or how fast they can travel compared to the atmosphere. And there are strong relations between these various time scales we saw and the waves that do the propagation of the disturbances in the system. So this is just showing examples of what are called easterly waves, which of course means going from east to west. So depiction of easterly waves in the Pacific Ocean in the 5 to 10 degree north. So you have to be careful here. The time is going from bottom to top, which is the usual for oceanographers, but sometimes atmospheric people go the other way. So this is using some satellite data visible imagery, what is called a Hofmöller diagram, where we looked at latitude or longitude and time. This is disturbance with wavelengths of 2500 to 4000 kilometers. So the wave length depends on various properties of the perturbation of the atmosphere, temperature gradients and background winds and so on and so forth, and they are propagating at speeds of the order of 8 to 10 meter per second. So here is the phase speed indicated by drawing lines to track the visible features from satellites, so that is a little bit approximate there. And then there is another section shown here going at different latitude from 0 to 20 degree north for the 3-day period of July 10 to 12 in 1967. Okay, so this is just examples of waves, a rich spectrum of waves in fact in the tropical atmosphere. But when we look at El Nino later on, we'll see that the ocean also has waves, and there are modulations of the waves by other waves. So you can see that this is now not so much a Hofmöller diagram, but looking at snapshots for July 10, 11 and 12 and trying to link the propagation of that particular feature with this phase speed indicating yellow line. The waves are also part of the systems that generate tropical cyclones, which are a warm water phenomenon, basically because a cyclone is set as a seed by rotation in the atmosphere, and if it begins to get energy from the ocean, it can grow by taking up moisture, condensing and building energy and growing stronger and stronger. And there are these locations where the cyclogenesis, or the seedlings being put by the system, which is closely related to convection in the atmosphere, happens. Of course, we heard about hurricanes in the Atlantic, typhoons in the Pacific Ocean, and cyclones in the Indian Ocean. The stretch available here is very different than the stretch here and the stretch here. And in the southern hemisphere, you can see that there are very few cyclones here climatologically in the long-term average, but the SPCZ region and the Indian Ocean region have a strong cyclogenesis happening. And with global warming, we are always worrying about whether cyclones are getting more in number, getting stronger, moving slower, carrying more water vapor, intensifying more rapidly, and so on and so forth. So this is just the frequency of tropical cyclonic storms per decade, and you can see that there is a strong hotspot here and a hotspot here over the West Pacific and South China Sea and over the Bay of Bengal, compared to the other regions of cyclogenesis and tropical cyclone. So there, cyclogenesis itself depends on MJOs, which move east west to east, as we said. It's affected by El Nino, La Nina, and there are other influences as well. So it depends on the vertical shear in the atmosphere, how winds change from the surface to the top, because the energy of the cyclone can be chopped off if the shear is strong. For example, in the North Indian Ocean, there is a pre-monsoon cyclone season, so March, April, May, and there is a post-monsoon cyclone season during October, November, December. But during the monsoon itself, even though there is a lot of convection, the shear is so strong that the cyclones do not occur during the monsoon season. Okay, that's kind of a very brief introduction. The other time scale we will look at in more detail is called the intraseasonal time scale that I already mentioned. The Madden-Julian oscillation is the most prominent intraseasonal feature. The monsoon intraseasonal oscillation is the other one. A classic paper from the 1970s by Madden and Julian started the process, and then there's been lots of efforts now to understand them and predict them better and understand their impacts, not only in the tropics but going all the way into high latitudes, mid latitudes, affecting potentially even the Arctic warming and so on. It's essentially showing convection here, sea level pressure here. So low sea level pressure basically means cooler temperatures, and warmer temperatures here corresponding to higher sea level. So convection moves eastward, so you can see there is convergence, and ahead of it there is sinking motion, clear skies, warming, and then it propagates. So as it moves eastward, sea surface temperatures get cooled by the convection, and there are many theories to explain why it moves eastward, at what speed it moves, what waves are involved, and so on. So you can see the genesis typically happens here in the western Indian Ocean. There are many issues involved in crossing the maritime continent, and by the time you get to the eastern Pacific, temperatures are cold, so there is no convection. So you can see that the signatures in OLR essentially disappears over there. Okay, so you can see convective phase, low OLR, dry phase ahead of it, sinking motion, high OLR, and you can see the clear eastward propagation here with the reorganization happening behind it. So don't worry about it, we'll come to all these details later on. We'll also learn about El Nino, which basically is the back and forth of the warm water that's climatologically here and the cold water that's climatologically here. For whatever reason, once in a few years, the cold waters here begin to be warmer because of reduced upwelling, and that begins to weaken the trade winds, begins to reduce the force that's holding the warm waters to the west, and the warm waters begin to slosh towards the east, and the convection that's here begins to slosh to the east as well. So you get anomalously cold temperatures here, anomalously warm temperatures here, which means you get the anomalously high pressure here, anomalously low pressure here. There are various indices we use to track the growth and the demise of the El Nino and so on. Southern oscillation is one where we look at the difference between pressure over Tahiti and Darwin, which was originally done by Walker. Then in the late 60s we figured out that that is also related to the ocean atmosphere interactions, and there are specific time scales there with the broad time spectra which we will see later on. Of course, always the question is how global warming is affecting these things. So there are other modes of variability at much lower frequencies, like the Atlantic multi-decadal oscillation, North Atlantic oscillation. You can see this tripole pattern here with this kind of time scale. This is basically measured as a pressure difference between Icelandic high and the Azores low, somewhere here. and this is measured as a sea surface temperature anomaly. You can see that this is a same sign over this whole region from the deep tropics to the higher latitudes, whereas this one has this tripole pattern, and the time scales are very different as well. Okay, this has got a multi-decadal time scale of 50-60 years. This has got a multi-year to multi-year to decadal time scale of something like 2 to 10 15 years. Okay, we will learn briefly about the stratospheric intrusions in the so-called quasi-biennial oscillations, where you can see that this is going into the stratosphere in the pressure level, and this is showing zonally average zonal monthly mean velocity, and you can see that it propagates down, so there is a clear time scale associated with it. It's a quasi-biennial time scale, but this also means there is a predictability to it. So when it starts here, you know that it's eventually systematically going to reach the surface. Okay, so the dynamics of this is somewhat well understood as well. Has to do with waves and the tropical, the stratospheric, tropospheric communications, gravity waves, and so on and so forth, that we will look at. It's called quasi-biennial because basically you can see that there is a approximately 2-year time scale here, 93 to 95, 95 to 97, and so on and so forth. Not always the same, but nonetheless you can see here it goes from 99 to 2002, hence it is quasi-biennial, and there are specific features and impacts associated with these that we will look at. Modes of the South Asian monsoon or the central northern Bay of Bengal. This is again looking at the period in days. We already talked about 2 to 10 day time scale, the quasi-biennial or 10 to 20 day time scale, and the 20 to 60 day time scale. This is from the trim rainfall. So this is basically a point that the high frequencies themselves are modulated by low frequencies. There are waves within waves, as we will see, with westward propagating features within eastward propagating envelopes that occur, and there are very interesting dynamics associated with those that we have to understand. Okay, it's kind of a quick run through the background. As I said, no need to panic, just listen to them, read the chapter, and then we will fill in the details of the dynamics, the ocean's role in these predominantly atmospheric phenomenon like MJO, or coupled ocean atmospheric processes like the El Nino and so on. Should be fun, so no need to panic.